Today's lecture concerns two risky businesses, war and insurance. We'll start off in World War II. In World War II, one of the challenges of the Allied intelligence officers was to estimate the strength of the German army. And in particular, one of the challenges was to estimate the number of Mark V tanks that the Germans had manufactured and were using in battle. Well, statistics played an heroic role in this quest for the number of tanks. So our lecture begins then on the battlefields of World War II. During World War II, when a German tank was captured, people began to notice that the tanks had serial numbers on them. And after capturing several of the tanks, the Allied forces, Allied intelligence officers began to suspect that the serial numbers were simply consecutive numbers starting at 1 and increasing as each new tank was built. And possibly, the German order was evident in their choice of serial numbers on the tanks. So statisticians approached this situation as a statistics question. And just think about it. This is exactly the realm of statistical inference. Namely, we know some information about part of the population, and we wish to infer information about the whole population. So we know that there are tanks numbered from 1 to N. Let's call N the total number of tanks in the German army, these Mark V tanks. So let's make the assumption that the tanks are captured as a random sample from the whole population of tanks. And what we would like to do is take that information about that random sample and estimate the total number N of tanks in the whole German army. So what we're going to do in this lecture is to look at different methods or strategies for calculating that estimate. And a method for estimating something is called an estimator. So we're going to look at different estimators for this problem. So let's start off with a specific example. Suppose we've captured 5 tanks, and the serial numbers on those tanks were 68, 35, 38, 107, and 52. So those were the 5 tanks that we captured. Question: what estimate should we make for the number N of the total number of tanks in the army, if that was the sample we had? Well, let's think about it as an abstract problem. Namely, the problem is exactly the same as if we had a big bag of poker chips, and each chip had a number on it, 1, 2, 3, 4, 5, up to some numbers, but we don't know how many. And then we reached into the bag and took out 5 of them. And then the numbers on those chips were those 5 numbers that we just said. And so the question is, how would we make an estimate for the total number of chips in the bag? You see, it's exactly the same question. Okay. Well, so let's think about different strategies of making their estimate. What would be a reasonable way to do it? Well, one idea that we've seen many times in the past lectures is that when we have a sample from a population, if we take the mean of the sample, then the mean of the sample is an approximation to the mean of the whole population. So maybe we could use that concept to make an appropriate guess for the number of tanks. And we discussed this kind of idea many times before. For example, when we estimated the average height of males by taking a sample of 5 or 10 or 100 males and taking the mean of that sample, that was an estimate of how tall an average male was in the country. Or the same thing with the proportion of voters for a different candidate. We'd take a sample, we'd see what the sample was like in terms of proportion of voters, and then we estimated what the total was like on that basis. So anyway, the idea is that the mean of the whole population is estimated by the mean of the sample. So since the mean of the numbers from 1 to N, in other words, if you just take all the numbers, 1, 2, 3, 4, 5 up to N, what's the mean of that number? Well, it's N plus 1 over 2. So doubling the sample mean would give 1 more than n. So let's just work it out here. The sample mean, x bar, remember x bar is the notation for when we take the mean, add up the numbers and divide by the number we have, will be approximately n plus 1 over 2, which is the whole population mean. So just doing the algebra, we see that n, which is the total number of tanks, that the number which we're trying to estimate, n, is going to be approximately equal to, multiplying through by 2 and subtracting 1, n will be approximately equal to 2 times the sample mean minus 1. So in our particular example, let's go ahead and do the arithmetic. This 2 times the sample mean minus 1 is 2 times, well, now this quantity right here is the sample mean, adding up the numbers and dividing by 5, subtracting 1, gives us the estimate 119. So this doubling the sample mean minus 1 is an estimator. It's a strategy for estimating the number of tanks. And it makes sense. It makes sense because it reflects the fact that the sample mean should be close to the actual mean. But there are other methods that we might consider doing. Let's try another method. Another method to estimate the midpoint of the numbers from 1 to n would be to take the median of the sample, the median value of the sample. Once again, the median value of the sample should give us a number that is somewhat near the middle of the total population numbers because we're taking this random sample. So let's go ahead and try that. So doing the median number, we could just take the median number and basically multiply it by 2. That would be another estimator. For our particular example, these 5 numbers, the median, remember what the median is, you just put the numbers in order and take the middle value. So the median of the numbers 35, 38, 52, 68, and 107, that is the middle value, is 52. So 2 times 52 is 104. So the estimator of taking the median value and multiplying by 2 would give an estimate of 104 tanks in the German army. Well, let's think about this. I mean, that is a ridiculous estimate. That's clearly wrong. Why is 104 clearly wrong? It has a basic flaw. The basic flaw is that it estimated a number, namely 104, that was lower than the highest serial number of a tank that we actually captured. So we know that this strategy, the double the median strategy, doesn't necessarily give us an estimate that is credible. You see? And so in our actual example, we saw that it gave us a number 104, and we know there are at least 107 tanks. Well, let's consider whether or not our previous method suffered from that same flaw. In the previous method, remember our previous method? The previous method was to take the mean of the sample, to double the mean and subtract 1 to make our estimate. Would it suffer from that same possibility of producing a number that was actually less than the biggest tank number that we actually captured? Well, let's just think about that. Suppose that we captured an additional tank, and the additional tanks number was 300. So now we've captured 6 tanks, and here are their serial numbers. Then if we apply the estimator method of doubling the mean and subtracting 1, look what happens. We get 2 times the mean of all these numbers, divided, which is adding them up and dividing by 6, minus 1 is 199. Well, that's clearly wrong because, once again, 199 is less than the biggest tank number that we actually captured. So there's a flaw to our method. Even though the logic seemed very good, there's a flaw, namely that either of these 2 methods have the property that it's possible to yield a result from our estimator could yield a result that's actually less than the largest number we've actually captured, and consequently is definitely too small. So these two estimators are, although they're conceptually good ideas, they aren't the best possible way to do it. Well, so we have to think of a different one. Here's a different strategy. We could guess the midpoint of the total number of tanks by taking the biggest tank number we captured and the smallest number we've captured, taking their average and doubling that. See? So this would be doubling the midpoint between the highest and the lowest, and that method at least always produces a number that's largest, that's as large or larger than the biggest number in our sample. So that's good. It doesn't suffer from at least that flaw of the previous methods, which is to give an estimate that is definitely too small. Well, anyway, these various estimators each have good intuition behind them, but actually there are other strategies that are even better. And what I'd like to talk about now are what qualities would we look for among different methods, among different estimators, that might guide our decision about which reasonable sounding strategy would be the best one to use. Now, in a way, there's no single right answer as to what method will generate the best estimate. But we can ask the question, how would we evaluate strategies? How could we make statements about various properties that a method, an estimator, has that would make it more or less desirable? So let's use the tank example to ground a discussion of desirable qualities of methods of statistical inference. Well, one feature that a method could have for generating estimates, that is an estimator, that's the method that generates an estimate. One property it could have is that it could maximize the probability of choosing the sample that we actually got. So let's follow it through here. For example, suppose there were 500 tanks in the German army. It would be possible, but very unlikely, to have randomly captured the 5 tanks of our original examples, numbers 68, 35, 38, 107, and 52. And the reason it's so unlikely is because all of those 5 numbers are so much smaller than the 500 possible numbers that it's unlikely that you would have found only those relatively small numbers. In fact, if there were 1,000 tanks, getting those particular 5 numbers would be even less probable. But if you had fewer tanks, then the probability of getting those 5 numbers becomes larger. So we might ask ourselves, what number of tanks in the German army would maximize the probability of our having gotten those exact 5 numbers, the numbers we actually got? For example, if there were 200 tanks, we'd compute the probability of getting those 5 numbers. Or if there were 150 tanks, we'd compute the probability of getting those 5 numbers. So in theory, we could do that analysis for every possible number of tanks and see which number gave us the largest probability. Well, I'll tell you the answer, because the answer actually is very simple, but very unsatisfying. The answer is that if the number of tanks is 107, namely the largest number among the tanks we actually captured, then the probability of choosing those particular 5 numbers is highest than, is higher than any other number of tanks you could have. And the reason is very simple. It's because if you're just selecting any particular set of 5 numbers from a total set of numbers, well, the smaller number of numbers you start with, the better chance you have of picking any set 5. But our intuition tells us that we're not likely to have captured the last built tank. So our intuition is that a good estimator would somehow have to estimate a number that's larger than the biggest number among the tanks we actually captured. So in this case, this maximum likelihood estimator, as the estimator is called, that is the one that maximizes the probability of having gotten the sample we actually got, doesn't seem to be reasonable. because it would just guess the biggest number that we got. Well, so statisticians have defined several qualities that an estimator may or may not have as a way of formalizing our intuition about what makes a good estimator. And one property that we might want a method to have is that if the method is performed many, many times, that is, if we took many samples of 5 tanks, and in each case evaluated our estimate of the total number of tanks using whatever method we're discussing, we might want it to have the property that, on average, the estimates that it produced would, in fact, be the true average of the number of tanks. And the average, by which I mean actually the mean of the estimates, is called the expected value of the estimator. The expected value of the estimator is the mean of all possible answers you would get by using that estimator for all possible samples, in this case of five numbers. Well, an estimator whose expected value is the correct value is called an unbiased estimator. If we use the estimator that just gives us the maximum of the samples that we chose, in other words, if we use the estimator where we just capture tanks and we guess that the number of tanks is the biggest number in that group, then that estimate is certainly not an unbiased estimator. And so let's be concrete about this. Let's be concrete about this and suppose that we have a certain number of tanks in the Army, N, and we randomly choose 5 tanks and we compute the estimator. And for example, our estimator is to just take the maximum of those 5 numbers. Well, if we imagine doing this for all samples of size 5 from the total N tanks in the whole Army, then if we take the average, the mean of all those maximum values, we certainly wouldn't get N, because no estimate using that method would ever be bigger than N, and most sets of 5 would have the maximum number smaller than N. So certainly the mean of all those sets of 5, of the maximums of the sets of 5, would certainly be less than N. So that estimator of just taking the maximum of the sample is not an unbiased estimator. On the other hand, the 2 times the sample mean minus 1 estimator is an unbiased estimator. You see, it had other defects, but it is an unbiased estimator because, remember, we saw many times before that the sample mean is an unbiased estimator of the population mean, meaning that when you take samples of size 5, their means, if you take all the samples of size 5, the mean of all those means is the same mean as the whole population. But we saw that estimator, the 2 times the mean minus 1, had other drawbacks, namely it produced values that were definitely wrong, not big enough. But on average, at least it's right. See, so on average it's right, but sometimes it's definitely wrong. Well, can we think of a strategy, an estimator, that's unbiased and yet gives us answers that never gives us an answer that's definitely wrong? And the answer is yes, we can. So here is another estimator that will turn out to be an unbiased estimator and a very good estimator. So here's the idea. The idea is that when we choose a certain number of tanks from our randomly selected group, we would expect the highest number of the tank that we actually captured to be somewhat less than the maximum number. And what we're going to do is try to estimate how much less. Well, let's just look at an example. Suppose that we had the actual number of tanks in the population were 1 through 7. That's the total number of tanks. And we selected 3 at random. Well, if the 3 at random were evenly spaced, our maximum number would be 6. So if we take 6, multiply it by some fraction to get it up to 7, in other words, we're trying to make it bigger, we're going to guess a number bigger than 6, and we're asking ourselves, how much bigger should we choose? Well, the answer is if we multiply 6 times 4/3, because you basically are dividing this range between 1 to 7 into 4 parts, and you're going to take a third of them and add an extra one, then subtract 1, you get 7. So here is that's sort of a little bit of just vague intuition about the reason for choosing the estimator of taking the maximum tank number that we actually capture and multiplying it by k plus 1 over k, where k is the number of tanks in our sample that we captured. So we're trying to estimate how much to augment the maximum tank we captured in order to make a good estimate of the total number of tanks in the Army. So we'll multiply it by a number that's slightly bigger than 1, namely k plus 1 over k. Multiply what by it? Well, multiply the biggest tank we captured, the serial number on the biggest tank we captured, that's the maximum, and then subtract 1, because that fits in with the previous example gives us a good estimate. So in our example that we had of these 5 tank number captured, we would multiply that maximum number, namely 107, by 6/5, because we captured 5 tanks, so k is 5, so we have 6 over 5 times that maximum 107 minus 1, it gives 127.4. So that would be our estimate for the number of tanks using this estimator. Well, this method of estimating tanks is an unbiased estimator. That is, if we use this computation on every possible sample, then the average of those estimates will in fact be n. The expected value of the estimator is n, which is the quality that we're looking for in an estimator for it to be an unbiased estimator. Now, of course, we certainly can't be sure that it's going to give the correct value, but the mean of the answers that it gives will in fact be the correct value. And we've done some simulations here. So here was a case where we took 3,000 tanks as the actual number of tanks. And from those, we took samples of size 100, meaning that we imagined that we captured 100 tanks at random. And for each of those captured tanks, we looked at the maximum number of all those 100, multiplied it by 101 over 100 to get a bigger number, and then subtract 1 to get an estimate. And we did that process, that whole process, 1,000 times, just as a simulation. So this is a computer simulation. We did it 1,000 times, as though we were fighting World War II 1,000 times. And here were the estimates that we got, given as a histogram. The minimum was 2,803 of our estimate, when the reality was 3,000, you see. And then the median was 3,010, the maximum was 3,030, and the mean, as prophesied, was extremely close, 3,001. Because remember, it's an unbiased estimator, meaning that on average, the mean of the estimates that it gives tend to be exactly right. And sure enough, here's an example where it was. I mean, this is simulations that suggest that that it is in fact an unbiased estimator. Well, another desirable quality we want in an estimator is to have as small a variance as possible, because that would mean that not only are the estimates close to the correct answer, but they don't vary too much from each other. So we actually are looking for an estimator that is not only an unbiased estimator, meaning that on average it gives us the right answer, but also that it has small variance, meaning a small standard deviation. And this estimator of taking k plus 1 over k times the maximum minus 1 is an unbiased estimator that has actually the smallest variance of estimators we can have. And in our simulation here, we had a standard deviation of 30 that's saying how spread out our guesses actually were. The idea being, of course, that if the variance is small, then we have a high likelihood that when we use the estimator, we'll actually get an estimate that's close to the actual value of n. The study of tanks has brought up the idea of expected value, which is a central idea in the other risky business of buying and selling insurance. So insurance is a way of tempering the vagaries of a risky life, and the whole concept of insurance is based on statistics. We can view insurance as a game of chance. where we determine the value of insurance as the expected value of the return. But of course, our decision to buy insurance or an extended warranty on a product or health insurance are based on a lot of other issues besides just the expected value of the return. It's a method by which we can make sure that our risk is not, we're not going to suffer great calamities. But the problem with insurance is that insurance always involves large numbers and scarce events, which people are not good at gauging in an even-handed way. And it makes it difficult for us to evaluate issues about insurance. For example, how much is an appropriate amount for an insurance policy to charge? Let's look at an insurance company that is insuring us against choosing the queen of spades from a deck of cards. So suppose that we have a deck of cards and the insurance policy is the following, that people are going to take this deck of cards and choose a card. If they choose the queen of spades, then the insurance company has to pay them $100. See, very simple insurance. The question is, how much money should the insurance company have on hand to know that it can pay off all the possible claims, and also how much should it charge for the insurance in order to make money on its as an insurance company? Well, our strategy is that we look at the distribution of possible numbers of winners out of these 1,000 players. It's possible that no one will choose the queen of spades. But it's possible that in fact all 1,000 people will choose the queen of spades. Well, in which case the insurance company goes broke. But the point is that we can look at the distribution of the likelihoods of 1,000 people, of how many out of those 1,000 are likely to choose the queen of spades. It's going to be centered at about 1/52nd of 1,000, because there are 52 cards in the deck, and you have one, each player of the 1,000 has a 1 out of 52 chance of picking it. But we can see this distribution that shows us that, generally speaking, the number of people likely to choose the queen of spades will vary between about 10 and 30. So if we want to be 98.7% sure of staying in business, we can have our insurance company have enough money on hand and charge high enough premiums so that it can pay the claims for 29 or fewer winners, because that's how many winners being the people that you have to pay off. That will account for 98.7% of the time. When buying insurance about products, for example, extended warranties, when you go into a company and you buy an electronics item, they'll always try to sell you an extended warranty. In that case, it's important not only to know the average time to failure of your electronic device, but in fact the distribution of those times to failure. And let me just show you a chart. Suppose that this is the chart of the time to failure of some electronic device that you're buying. And you're trying to decide, should I buy the extended warranty? Well, the advertisement will say on average, the time to failure is right here. And so you should buy the extended warranty. But in fact, the distribution of times to failure may look more like this graph, in which case, this is the likely location of the two important moments. One is the end of the manufacturer's warranty, which is when things fail because of some manufacturing defect. Then once an electronic item is going, it works pretty well for a while. And then right about here will be the end of the extended warranty period, at which time a lot of these devices will break. At least this is the common experience of many people in trying to decide whether or not to buy the extended warranty. Well, it's been my pleasure today to talk to you about risk in the two areas of war and insurance.